today we'll start with a new chapter, that is hydrocarbons. In today's chapter we will see about introduction of hydrocarbons and what are alkanes. Now the name itself says hydrocarbons. Now here you will learn all the compounds that involves hydrogen and carbon. So here basically the compounds which are made up of hydrogen and carbon are involved. Okay, hydrocarbons basically are the compounds made up of hydrogen and carbon as a base of them. Something similar to your carbon and its compounds. Hydrocarbons, the term hydrocarbon is self-explanatory, which means compounds of carbon and hydrogen only, as I told you initially. Now hydrocarbons play a key role in our daily life because most of the things in our daily life is made up of carbon and hydrogen because they are present abundantly in our environment. Now you must be familiar with the term LPG and CNG used as a fuel. You know, right? LPG and CNG. LPG is liquefied petroleum gas, whereas CNG stands for compressed natural gas. Now, another term LNG, that is liquefied natural gas, okay, is also in news these days. Even though LPG, every house has an LPG cylinders, right? For cooking purpose we use LPG gases, that is a liquid petroleum gases. Then in vehicles nowadays we started using CNG for vehicles, that is compressed natural gas. Another term which is very familiar these days is LNG, that is liquefied natural gas. Okay, now this is also a fuel and is obtained by liquefaction of natural gas. Okay, CNG is compressed natural gas. When you liquefy the natural gas, it is LNG, okay, which is also a fuel and we still use it. Now, petroleum, diesel and kerosene oil are obtained by the fractional distillation of petroleum found under the earth's crust. Now petroleum, diesel and kerosene, these are some of the hydrocarbons, okay. And fuel system which we use, right? Petrol and diesel we use for vehicles and all. So these are the fuel or oils which are obtained from the earth's crust, okay. It is obtained from earth's crust with the process called as fractional distillation. You will learn about fractional distillation in the organic chemistry and its some techniques in which fractional distillation is also involved, okay. In the chapter organic chemistry, some basic principles and techniques, in that chapter you will be learning about distillation and fractional distillation. So petroleum and diesel are the example using which were derived or obtained by fractional distillation of petroleum. Now coal gas is obtained by the destructive distillation of coal, okay. Again, a destructive distillation of coal will give you a coal gas. Now natural gas is found in upper strata during drilling of oil wells. So when you drill an oil well on the upper part, okay, you will get a natural gas. Now LPG is used as a domestic fuel with the least pollution. So LPG that we use at our home, it is used as a domestic fuel. Domestic fuel means we use it at home and it has a very less pollution. Kerosene oil is also used as a domestic fuel, but it causes some pollution. Kerosene, you know, we for chulas and all, we use kerosene oil so that the wood should burn. We drop little oil and then we burn the woods, right? So kerosene oil, even though it is used in a domestic purpose, but it does have a pollution. It can cause pollution. Now automobiles need fuels like petrol, diesel, and nowadays we use CNGs. Now petrol and CNG operated automobiles cause less pollution. So whichever vehicle which uses petrol and CNG, that is compressed natural gas, as a source of their fuel, they causes less pollution. Now all these fuels contain mixture of hydrocarbons which are source of energy. So all these fuels, whether it is LPG, CNG, LNG or petrol, diesel, anything, all of them contains hydrocarbons because they are the source of energy. Now hydrocarbons also used for the manufacture of polymers like polythene, polypropylene, polystyrene, etc. Now hydrocarbons, they are also used in the manufacture of polymers like polythene bags we have, right? Polythene, polypropylene, polystyrene, these are all hydrocarbon compounds which are used by us. Higher hydrocarbons are used as solvents for paints. Now They are also used as the starting materials for manufacture of many dyes and drugs. So hydrocarbons have various uses. Okay, they are abundant in our environment and they are used in lot of industries and areas. Okay, now thus you can well understand the importance of hydrocarbons in our daily life, because whatever we use in our daily life has hydrocarbons in it. So this chapter is basically to understand what are these compounds. Now classification. Hydrocarbons are of different types. Okay, hydrocarbons you can classify them into different types depending upon the types of carbon-carbon bond present. They can be classified into three main categories. Okay, now hydrocarbons is, as you know, there are different types of hydrocarbons. Now how they are classified? They are classified on the basis of the carbon-carbon bonds which are present, and they are classified into three main categories. Okay, now first one is your saturated. First one is saturated, second is unsaturated, and third is aromatic hydrocarbons. So you have saturated hydrocarbon, unsaturated hydrocarbon, and aromatic hydrocarbons. Now, saturated hydrocarbon contain carbon-carbon and carbon-hydrogen single bonds. Now, saturated hydrocarbons means you will have all the single bonds. Okay, between carbon-carbon also there will be a single bond. Between carbon-hydrogen also there will be a single bond. Now, if different carbon atoms are joined together to form open chain of carbon atoms with single bonds, they are termed as alkanes. So as you know, we have alkanes, alkenes, and alkynes. Now when we join different carbon atoms, when we join together to form a chain of carbon atoms, now all this chain should have a single bond in them. However, how many carbon atoms you are joining, but it should be joined with a single bonds. They are termed as alkanes. So alkanes are basically carbon-hydrogen long chain with single bond in it. Okay, and they are example of saturated hydrocarbon. On the other hand, if carbon atoms form a closed chain or a ring structure, they are termed as cycloalkanes. Similarly, if the long chain structure is there, it is alkanes. But those long chain structure, if we convert them into a cyclic structure means, for example, propane, CH3, CH2, CH3. Okay, this is a propane. This is an alkane. This is a straight chain structure. But this straight chain structure, if I convert it to a cyclostructure means CH3, CH3, CH2. Okay, this is a cyclic structure where I am forming a triangle. Okay, now these are called as cycloalkanes. Okay, with single bond, they are called as cycloalkanes. Now these are saturated hydrocarbons. Now what are unsaturated hydrocarbons? Containing carbon-carbon multiple bonds, double bond, triple bond, or both. Aromatic. Okay, so if saturated hydrocarbon is carbon-carbon single bond or carbon-hydrogen single bond, then unsaturated hydrocarbon means carbon-carbon will have a multiple bond, either a double bond or a triple bond, or it can have both double and a triple bond involved in the same molecule. That is an unsaturated hydrocarbon. Now this double or triple bond can be present with any molecule also. It's not always true that the double bond or triple bond should be present between carbon-carbon. You can have them with any other functional groups also. Those are all called as unsaturated hydrocarbons. Now aromatic hydrocarbons are a special type of cyclic compounds. Now aromatic hydrocarbons are a special type of cyclic compounds. They are cyclic compounds. Okay, they are cyclic compounds, but they are special. You can construct a large number of models of such molecules of both types, open chain and closed chain, keeping in mind that carbon is tetravalent and hydrogen is monovalent. You can form large number of models. Large number of models means you can join any molecule anywhere. Now you can have a molecule with 4 carbon-carbon bonds, 5 carbon-carbon bonds, 6 carbon-carbon bonds. So you can have a chain of structures with n number of carbon-hydrogen bonds. Okay, but if you form them, you have to keep in mind that carbon is tetravalent and hydrogen is monovalent. So you should not join any other molecules to them once their valencies are satisfied. For making models of alkanes, you can use toothpicks for bonds and plastic plasticine balls for atoms. So to bomb, if you want to make a 3D model of alkene, okay, you can use a ball, okay, a ball made up of plastic or a ball made up of thermocol, and to that you can use the toothpicks depicting the bonds, single bonds. Okay, for alkynes, alkenes and aromatic hydrocarbons, spring model can be constructed. Okay, now what is alkenes? Now, first we will start with alkenes, then we'll go to alkenes and alkynes, and last we will deal with aromatic hydrocarbons. So let's start with alkenes today. Now alkenes, as already mentioned, alkenes are saturated open chain hydrocarbons containing carbon-carbon single bond. So initially when I was explaining saturated hydrocarbons, I have explained you that alkenes are the saturated hydrocarbons with single bond between carbon and carbon. Now, a basic example is your methane, okay, is the first member of this family. Okay, methane is the first member of the alkenes family. Now methane is a gas found in coal mines and marshy places. Where you can find methane? Methane you can find in coal mines and marshy places. And also you can prepare methane gas at your house also. You have a biogas plant, right? You add all the waste slurry into a biogas plant. Now the biogas which is produced or which is evolved is your methane gas. Okay. If you replace one hydrogen atom of methane by carbon and join the required number of hydrogens to satisfy the tetravalency of the other carbon atom, what do you get? Now, if you have a carbon, okay, and to this carbon I am adding 4 hydrogens because carbon has a tetravalency, so it can form 4 bonds, right? Now you have added hydrogens to satisfy the tetravalency of the carbon. What do you get? You get this structure. This is called as methane structure. Now you get C2H6. Now another thing. Now I have 2 carbons joined with a single bond. Now 1, 2, 3 and 4. This carbon is satisfied. 1, 2, 3 and 4. This carbon is also satisfied. The remaining places I am adding hydrogens. Okay, remaining places I am adding hydrogens. Now what it is formed? C2, 1, 2, 3, 4, 5, 6, H6, C2H6. This is ethane. Now similarly, 1, 2, 3. I have added 3 carbons. 1, 2, 3. Tetravalency is satisfied. 1, 2, 3, 4. Again this carbon is satisfied. 1, 2, 3. This carbon is also satisfied. Remaining places add hydrogens. Now here 1, 2, 3. C3. 1, 2, 3, 4, 5, 6, 7, 8. H8. This is propane. Okay. Like this you can form alkanes. Now this hydrocarbon with molecular formula C2H6 is known as ethane. Thus you can consider C2H6 as a derived form of CH4, because from CH4 you have removed one hydrogen. In place of that hydrogen you have added one carbon, and to that carbon, to satisfy the tetravalency, you have added 3 hydrogens. So like this you have derived C2H6 from CH4 by replacing one hydrogen atom by a CH3 group. Okay, now go on constructing alkanes by adding this theoretical exercise, that is replacing hydrogen from hydrogen atom by CH3 group. The next molecule will be C3H8. Next one will be C4H10. So like this you can go on adding. Now how I formed C3H8? I have removed this hydrogen. In place of this hydrogen I have added another CH3 molecule. Now again do the same thing. Remove this hydrogen, add another CH3 group. You will get C4H10. Like this, adding CH3 groups at the end, removing one hydrogen from the end and adding CH3 group. Again remove one hydrogen from the end, add CH3 group. By doing this you can construct a large number of alkanes. Now, these hydrocarbons are inert under normal condition as they do not react with acids, bases or other reagents. So these molecules, these hydrocarbons are inert. Inert means they doesn't react with acids, bases, nor with any other reagents. Hence they were earlier known as paraffins. Since they doesn't react with anything or they are inert, earlier they were known as paraffins. In Latin, param means little, affins means affinity. So paraffin means little affinity. Now, can you think of the general formula for alkane family or homologous series? Now, if you know right how alkanes can be formed. From methane, remove one hydrogen, add a CH3 molecule. From that CH3 molecule, remove one hydrogen, add another CH3 molecule. So like this you form a chain. Like this how you will form an alkane. Now how you will write a general formula? If we examine the formula of different alkanes, we find that the general formula of alkanes is CN2N plus 2. Okay. So how you will write the general formula? CnH2n plus 2. Now how you will solve? For example, for propane we will take. Propane is 3 carbons, right? C3H 2 into 3 plus 2. Now 2 into 3 is 6. 6 plus 2, 8. So what is the formula earlier we had done? It is C3H8. So this is how we calculate the formula for alkanes. This is the formula, that is CnH2n plus 2. Now it represents any particular homologue when n is given appropriate value. So this will represent any particular homologue when your n value is given appropriately. Now according to VSEPR theory we have learned in a previous videos. Now methane has a tetrahedral structure in which carbon atom lies at the center and the 4 hydrogen atom lie at the 4 corners of the regular tetrahedron. So here from VSEPR theory we have learned about the shapes and structure, geometry of the compounds, right? So according to VSEPR theory, for methane you have carbon at the center and 4 hydrogens are present at the 4 corners, right? So it forms a tetrahedral structure. Now in alkanes, tetrahedra are joined together in which CC and CH bond lengths are 154 picometers and 122 picometers. So in alkanes, basically you form a tetrahedron. Okay, the tetrahedra are joined in such a way that your carbon-carbon bond is 154 picometer and carbon-hydrogen bond length is 112 picometers respectively. Now you have already read that CC and CH are sigma bonds. Why sigma bonds? They are single bonds. So they are sigma bonds and are formed by head-on overlapping of sp3 hybrid orbitals of carbon and 1s orbitals of hydrogen atoms. Now this we have learned in our previous chapter, that is chemical bonding. There we have seen that carbon-carbon and carbon-hydrogen they form a sigma bond, and alkanes they basically show sp3 hybrid orbitals and they have a head-on overlapping between carbon and 1s orbital of hydrogen atoms. Next is nomenclature and isomerism. Now you have already read nomenclature of different classes of organic compounds, right? Now in organic compounds we have seen nomenclature. Nomenclature and isomerism in alkanes can further be understood with the help of few more examples. Now how you will name them? Now common names are given in parentheses. Now you have, for organic compounds you have a common name and you have an IUPAC name. IUPAC is an International Union for Pure and Applied Chemistry. Now, that is an organization who deals with all the chemical compounds, or all the field of chemistry is dealt by them. Whichever new compound or new element you discover, you have to submit a paper to the IUPAC. They will decide the name, select the name and give the compound appropriate name. So all these names were certified by IUPAC. Now, first 3 alkanes are methane, ethane and propane. Okay, meth, eth and prop have only one structure, but higher alkanes can have more than one structure. So these 3 are the basic and they will have only one structure, but above them, okay, above propane the structures can have more than one form. Okay, Let us write the structure of C4H10. Okay, 1 2 3 4 4 carbons, 1 2 3 4 5 6 7 8 9 10 10 hydrogens. So this is the structure of C4H10. Now 4 carbon atoms can be joined either in a continuous chain or with a branched chain in the following two ways. Okay, so C4H10, it can be shown in two structural format. First, it can be shown in a straight chain form. Okay, so this is butane or N-butane. Now the name of 4 carbons is but. ANE stands for single bond, so it is a butane. This is the first structure. Second structure, you can show them in a branched format. Branched format means CH3, CH, CH3, CH3. Again 1 2 3 4 4 carbon. Okay, now this is also a C4H10 molecule. Okay, but the name will change to 2-methyl propane. Why 2-methyl propane? On the second carbon you have a methyl group, so and this is a propane group, so it is 2-methyl propane. Or another name for this, since it is C4H10, you can name it as isobutane. But isobutane because on the central position you have a methyl group, so this is an isobutane. Now in how many ways you can join 5 carbon atoms and 12 hydrogen atoms of C5H12? Now C5H12, you can show them in 3 structural format. First is the simple straight chain format. This is pentane or N-pentane, where you will join all the carbons in a straight chain. Next will be your branch chain format. Branch chain format means CH3, CH, CH2, CH3, and on this carbon you have a CH3 group. Again 1 2 3 4 5 carbons are involved, so this is C5H12. But while naming, it will become 2-methyl butane. 1 2 3 4, this is butane. On second carbon you have a methyl group, so it will become 2-methyl butane or isopentane. Why? On the second carbon you are joining the CH3 molecule, so it is isopentane. Another form of arrangement for this pentane molecule is you can join them in since I can show them in 4 carbon, I can show them in 2 carbon also. CH3C, CH3, 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 1 2 3 4 5 carbons. Now 1 2 3, so this is 2,2-dimethyl propane. That means on the second carbon you have 2 methyl groups that are joined, so it is 2,2-dimethyl propane. Why propane? 1 2 3 carbons are involved. Now again this can be named as neopentane. Why neopentane? On the second carbon you have 2 methyl groups that are attached. It forms a neo structure. So these are the different kinds of structures and names. Now structure 1 and 2 possesses same molecular formula but in their boiling point and other properties. Okay, the structure 1 and 2, they possess almost same molecular formula, that is C5H12, but there is a difference in their boiling and melting boiling point and other properties. Why? Even though they have same C5H12 molecular formula, but the arrangement is different. This is a straight chain, this is a branch chain. The arrangement differs, and because of this different arrangement you will have a different boiling point and some of their properties will differ. Now, similarly, structure 3, 4 and 5 possesses the same molecular formula but have different properties. Same thing with other molecules also. Now, structure 1 and 2 are isomers of butane, whereas structure 3, 4 and 5 are isomers of pentane. So here these two structures, structure 1 and 2, these are isomers of butane, and these 3 are isomers of pentane. Why? They have same molecular formula but different properties, so they became isomers. Now since difference in property is due to the difference in their structure, they are known as structural isomers. Okay, now what type of isomers they can be? They are structural isomers. Why structural isomers? They have same molecular formula, but their structure changes, and the property change is due to their difference in structure. Hence, they are structural isomers. Okay, and they are known as structural isomers. It is also clear that structure 1 and 2 have continuous chain of carbon atom, but structure 2, 4, 5 have a branched chain. Now, what is the difference between their structure? 1 and 3. Okay, 1 and 3 are, this is structure 1, which is a straight chain. Again, this is structure 3, which is a straight chain. Both are straight chains, but the remaining structure 2, 4 and 5, they have a branches in them. So there is a structural change, even though their molecular formula is same. Now, structural isomers which differ in chain of carbon atoms are known as chain isomers. Okay. Now, structural isomers which differ in chain of carbon are known as chain isomers. Thus, you have seen that C4H10 and C5H12 have 2 and 3 chain isomers respectively. Okay, so you can have, what is chain isomers? Now, this is your pentane, 1 2 3 4 5, 5 carbon का chain, 1 2 3 4, 4 carbon का chain, but still this is a pentane. 1 2 3, 3 carbon का chain, but still this is a formula for pentane. So these are called as chain isomers. Now, based upon the number of carbon atoms attached to a carbon atom, the carbon atom is termed as primary, secondary, tertiary or quaternary. Now, based on the number of carbon atoms that are attached, okay, you can have a primary, secondary, tertiary or quaternary structure. Now, carbon atom attached to no other carbon atom, as in methane, or to only one carbon atom, as in ethane, is called primary carbon atom. Now, what are primary carbon atom? Primary carbon atom example they have given as methane and ethane. That means primary carbon atom means the carbon will either attach to one carbon or it won't be attached to any carbon. Okay, when a carbon atom, okay, has no other carbon atom attached, or it has a single carbon atom which is attached, for example methane and ethane, these are called as primary carbon atom. Okay, now terminal carbon atoms are always primary. So the terminal carbon atoms, that is your CH3 molecules, they are always primary. Carbon atom attached to two carbon atoms is known as secondary. When you have a carbon atom which is attached to two other carbon atoms, this is a secondary structure. Tertiary carbon atom means you have a carbon atom which is attached to three other carbon atoms, is called as tertiary carbon. And neo or quaternary carbon means you have a single carbon atom which is attached to four different carbon atoms. This is called as quaternary or neo carbon atom. Okay, now can you identify primary, secondary, tertiary and quaternary carbon atoms in structure 1 and 5? Let's see. In structure 1, this is your primary carbon and this is also your primary carbon, because they are terminal carbons attached to one carbons. Now, this and this, both of them are secondary carbons because they are attached to two different carbons. Okay, this is attached to this carbon and this carbon also. This is attached to this carbon and this carbon also. These two become secondary and these two become primary. Next, in fifth structure. In fifth structure, this is your quaternary carbon. By quaternary carbon, this carbon is attached to 1, 2, 3, 4 carbon atoms. Okay, this one will become primary. This will become again a primary. This is also primary and this is also primary. Okay. Now, if you go on constructing structures for higher alkanes, you will be getting still larger number of isomers. So as you go on making more and more alkanes, you will get more number of isomers. Okay, for example, C6H14, that is your hexane. Hexane has got 5 isomers. Your okay, hexane, you will have methane, ethane, propane, butane, pentane, hexane, septane. Your septane, octane. Okay, all these molecules will have higher and higher number of isomers. Your septane has 9. As many as 75 isomers are possible for your decane. So C10H22, that is your decane, and this decane can form 75 isomers. So in structure 1, 2 and 5, you observed CH3 group is attached to carbon atom numbered as 2. Now you will come across groups like CH3, C2H5, C3H7, etc. attached to carbon atoms in alkenes or other classes of compounds. These groups of substituents are known as alkyl groups. Now what are alkyl groups? CH4, you remove one hydrogen, it will become CH3. C2H6, you remove one hydrogen, it will become C2H5. Now this is methane, this is ethane. But the moment you remove one hydrogen from both of them, they become methyl and ethyl. So these are your alkanes and these are your alkyl groups. Okay, and these you can find as a functional group or substituting group on the carbon chain. Okay, so they are called as alkyl groups as they are derived from alkanes by removal of one hydrogen atom. Now general formula for alkyl groups are, for alkane it is CnH2n plus 2. For alkyl groups it will be CnH2n plus 1. We are removing one hydrogen. Okay. Now let us recall the general rules for nomenclature. The nomenclature of substituted alkanes can further be understood by considering the following problems. Now how you will name them? First you have to count the number of carbons, see on which carbon you have attached which functional group, and then you have to name them. Now, for example, here 1, 2, 3, 4, 5. So this is a pentane. Now to that I have added one alcohol. So this has become pentane 1 all. So you have to number them in such a way that least number should be given to your functional group. So I'll start from here, 1, 2, 3, 4 and 5. This is pentane 1 all because on the first carbon you have an OH group. Now here I will start to number it from here, 1, 2, 3, 4, 5. Now why I started from here and here why I started from here? Because you should always try and give least number to the functional groups. So here it will be pentane 2 all because on the second carbon you have the alcohol. Similarly other molecules. Okay, this is how the nomenclature is. Now how you will start nomenclature of few organic compounds and remark. Now here you can see 4-ethyl 2-methyl hexane. Now on the 4 carbon you have an ethyl group, on the second carbon you have an methyl. Okay, so it is 4-ethyl 2-methyl hexane. Why hexane? 1, 2, 3, 4, 5 and 6. Now why you have given it like this? If I started numbering from here, okay, it will be 1, 2, 3, 4, 5 and 6. So in this case ethyl will become 3 and methyl will become 5. Is it better to have 2-4 configuration or 3-5 configuration? It's better to have a 2-4. So you have to always try and give least number to the functional groups. Okay, so lowest sum, that is least, and the naming is in the format of alphabetical arrangement. That's why ethyl came first and methyl came second. Okay. If it is important to write the correct IUPAC name for a given structure, it is equally important to write the correct structure from the given IUPAC name. So it is vice versa. If you have an IUPAC name, you have to write a correct structure. If you have a correct structure, you have to write a correct IUPAC name. It is equally important. Okay, and to do this, first of all, the longest chain of carbon atom corresponding to the parent alkane is written. So in this case, what we do is, here they have given an example as 3-ethyl 2,2-dimethyl pentane. Now here you know pentane is the parental structure or parent alkane structure. So first you have to write the parent alkane structure. Draw the chain of 5 carbon atom. Now here what we are doing is, we are writing the structure from the name. Till now what we had done? We had done writing name using the structure. With respect to structure, we were writing the name. Now we will be writing the structure with respect to their name. Okay, so to do that, we have to follow certain steps. Now in that first step is, always draw the parent alkane chain first, that is always given at the end. Okay, so pentane is your parent carbon chain. So 5 carbons joined together. Now give them the numbers 1, 2, 3, 4, 5. Okay, second step is numbering. Once you number them, now the name is 3-ethyl 2,2 3-ethyl 2,2-dimethyl pentane. Right? Now first we have drawn a 5 carbon chain, then we have numbered them. In third step, attach ethyl group at carbon 3 and 2 methyl groups at carbon 2. Now you have 3-ethyl and 2,2-dimethyl. So on the second carbon, you will attach 2 methyl groups, and on the third carbon you will attach the ethyl group. Once this is done, last step is that you have to satisfy the valency of the carbon. So here this carbon will have 3 hydrogens. No need to satisfy this carbon because 1, 2, 3, 4, it already has 4. 1, 2, 3. Here you have to attach 1 hydrogen. 1, 2, 2 hydrogens. 1, 2, 3. Last is the satisfying the valency of the carbon by adding the appropriate number or required number of hydrogen atoms. Now this is how you will write a molecular this is how you will write a structure from the name of the molecule. Okay, now next is the preparation. Now how you will prepare alkanes. Now petroleum and natural gas are the main sources of alkanes. Now however, alkanes can be prepared by following methods also. Even though petroleum and natural gas is the main source of alkane, but you can prepare alkanes in the laboratory. First one is from the unsaturated hydrocarbons. Unsaturated hydrocarbons means all your hydrocarbons with double or triple bond. Now dihydrogen atom adds to alkenes and alkynes in the presence of finely divided catalysts like platinum, palladium or nickel to form alkenes. So when you have dihydrogen, okay, dihydrogen means H2. So you can add H2 to your alkenes or alkynes. Alkenes means the molecule with double bond, alkynes mean the molecules with triple bond. Okay, so you can add dihydrogen to alkenes and alkynes, okay, in the presence of a catalyst. Okay, and the catalysts are platinum, palladium or nickel. In presence of either of this catalyst, you can add hydrogen to alkenes and alkynes to form your alkanes. Now this process is called hydrogenation. Why hydrogenation? Because you are adding hydrogen. And these metals absorb dihydrogen gas on their surface and activate the hydrogen bond. Now what happens? The metals like platinum, palladium and nickel, they are metals. Okay, what they do is they absorb the dihydrogen gas on their surface, okay, and activate the hydrogen bond. Now platinum and palladium catalyze the reaction at room temperature. Okay, platinum and palladium, you can use this catalyst at room temperature, but relatively higher temperature and pressure are required with nickel catalyst. So for using nickel, you want a temperature higher than room normal room temperature, and pressure is also required to use nickel catalyst, whereas platinum and palladium you can use them in a normal room temperature also. So how you can do that? Now ethene, okay, plus H2 in presence of platinum, palladium and nickel, what will happen is one of this bond will break. Okay, since this bond is broken, carbon will have 2 electrons given to them, because a single bond means there are 2 electrons which are involved. Once you break the bond, but the electrons will be taken up by the respective atoms. So carbon will take up both the electrons. Since you have 2 hydrogens, one hydrogen will join this carbon, one hydrogen will join this carbon. So it will become CH3, CH3. That is your ethane molecule. Okay. Now, next is your propene. Again same thing will happen. Your double bond will break and hydrogen will be added. Now in case of propine, that means you have 3 triple bonds. So in this case what you have to do is single H2 means you will be breaking one bond. Since there are triple bond, you will break one bond and you will add 2 hydrogens, but still there is a double bond which remains. So you have to break one more bond and add one more hydrogen pair. So it is 2H2 in case of triple bonds. Okay, and this is how you will form alkanes from unsaturated hydrocarbons. Now from alkyl halides. Now what are alkyl halides? Alkyl groups, you know, methyl, ethyl, propyl groups. To them you have to add an halogen. Now halogen is your X represented, and it can be chlorine, bromine or iodine. Either one of them is an halide. So here they have taken chloromethane. Okay. Now to this chloromethane, what you have to do is alkyl halides except fluorides. Okay, that's why I have given you chlorine, bromine and iodine. On reduction with zinc and dilute hydrochloric acid gives alkene. So you have to reduce the chloromethane, or you have to reduce the alkyl halide using zinc and hydrochloric acid. So in this case you will get methane and HCl gas. Now how HCl gas? Here you have 2 hydrogens, right? And you have CH3Cl. What will happen is one hydrogen will bind to the methyl group, another hydrogen will bind with the Cl. So it will give you CH4 plus HCl. Okay. Same thing everywhere you will get an ethane and hydrochloric acid will be released. Now, that is the first one. Second, you have to treat the alkyl halide with sodium metal in dry ethereal. Ethereal means free from moisture solution, give higher alkenes. This reaction is known as Wood's reaction and is used for the preparation of higher alkenes containing even number of carbon atoms. Now, where we use this process? This is called as Wood's reaction, when you react sodium metal in the moisture free condition. Okay, it will give you higher alkenes. Higher alkenes can give you a long chain alkanes. Okay, higher alkenes it can give you. Now in this case what you have to do is you have to take 2 compounds, okay, 2 molecules of bromomethane. If you are taking any compound, okay, bromoethane, bromomethane, you have to take them twice, and you have to take a sodium metal, and in presence of diether, okay, in presence of diether you will get ethane, because you will be removing this Br molecule and you will be combining this CH3 together, okay, and you will be taking out this Br molecule with the help of sodium metal. So NaBr will be released. So this is how you will be forming alkanes from alkyl halides, and this reaction is called as Wood's reaction. Now next one is from carboxylic acid. Now how you will prepare from carboxylic acid? First one is sodium salt of carboxylic acid on heating with soda lime, mixture of sodium hydroxide and calcium oxide, give alkanes containing one carbon atom less than the carboxylic acid. Okay, This process of elimination of carbon dioxide from carboxylic acid is known as decarboxylation. Now, what is this? You have a sodium salt of carboxylic acid. Okay, that means what is a carboxylic acid? CH3COOH. In place of H, when you add sodium, that is CH3COONA, this is sodium salt of carboxylic acid. Okay, when you heat it with soda lime, what is soda lime? Soda lime is a mixture of sodium hydroxide with calcium oxide. Okay, that is your soda lime. It gives you alkanes. Now what happens is that in this process you remove this COO compound. Okay, so COO means CO2, that is your carbon dioxide. So when you remove carbon dioxide from carboxylic acid, the process is known as decarboxylation. So here what happened, this COO minus is removed. Okay, and this hydrogen is added to this CH3 molecule, so it became CH4. So CH4, and then you have Na combining together forming Na2 and CO3, that is sodium carbonate, disodium carbonate is formed. Okay, this is what decarboxylation reaction is. Now containing even number of carbon atoms at the anode. So you have to have even number of carbon atoms. Now next one is your Kolbe electrolytic method. First you have seen decarboxylation method, next is your Kolbe's electrolytic method. Now an aqueous solution of sodium or potassium salt of a carboxylic acid. Again same thing, sodium salt or potassium salt of carboxylic acid on electrolysis gives alkane. So when you electrolyze, it gives you alkanes containing even number of carbon atoms at the anode. Now, this is sodium acetate or sodium salt of carboxylic acid plus electrolysis, so you have to have water molecule. When you electrolyze, you get CH3CH3, that means you have to add 2 molecules of sodium acetate with water. You have to mix them in water, you have to add the electrolytes, and you have to start the electrolysis process. In short, you will get a ethane molecule, you will get release of carbon dioxide, you will have release of H2, and you will have NaOH. This Na will combine with OH. Okay, this is what Kolbe's electrolytic reaction is. Now the reaction is supposed to follow the following path. That means this is what happens. Okay, so you have 2 sodium acetate molecule. Okay, so it is like this. This CH3CONA, you can write it as CH3C double bond O single bond O minus plus Na plus. Okay, this is how splitted. If you split it, this is how it will look. Now at anode, this CH3COO minus, this loses 2 electrons. Okay, and it will become, this is an acetate ion, it will become acetate free radical. It will lose 2 electrons. Okay, now once it loses 2 electrons, what will happen is this will break. Okay, once this break, you will have methyl ka free radical. If this bond breaks, 1 electron will go to methyl, 1 electron will go to carbon. So once this carbon attains 1 electron, it becomes carbon dioxide gas and it is released out. But the methyl radical will remain there, will become methyl free radical. So since you have used 2 acetate ion, you will get 2 methyl free radicals which will combine together to form ethane. Okay, this is what happens at anode. What happens at cathode? Cathode, you have water molecule, it releases 1 electron and becomes OH minus and H plus. Now both the H plus will combine and form H2, and this OH will combine and form NaOH. Okay, 2 molecules of NaOH which is later released. Okay, this is the mechanism of the reaction. Now next is the properties. Okay, now physical properties. Alkanes are almost non-polar molecules because of the covalent nature of carbon-carbon and carbon-hydrogen bonds, and due to very little difference of electronegativity between carbon and hydrogen atoms. So Alkanes are non-polar because they have a very stable covalent bond between carbon-carbon and carbon-hydrogen, and they are due to very little difference of electronegativity between carbon and hydrogen. Now, they possess weak van der Waals forces. So the force between them is very weak. Now, due to weak forces, the first four members C1 to C4 are gases. Okay, since they have weak forces, because of that, methane to butane. Okay, methane till butane, that is C1 to C4 are gases. C5 to C17 are liquids, and those containing 18 carbon atoms and more are solids at 298 Kelvin. So C1 to C4 are gases, C5 to C17 carbon 17. Okay, when you have chain of 17 carbons. Okay, C5 to C17 are liquids, and the ones which are from C18 to above, okay, are solids at normal room temperature. They are colorless and odorless. So all the hydrocarbon compounds, they are colorless and odorless. Now, petrol is a mixture of hydrocarbons and is used as a fuel for automobiles. Okay. Now, some of the hydrocarbons, they have solubility. Okay, petrol is again a mixture of hydrocarbon and it is used as a fuel of automobiles. Okay, petrol and lower fraction of petroleum are also used for dry cleaning of clothes to remove grease stains. So sometimes petrol and lower fractions, it is derived by fractional distillation, right? So lower fractions of petroleum, they are used for cleaning clothes or dry cleaning the clothes by removing the stains. Now, these are some of the physical properties. Grease, if you say that it is non-polar and hence hydrophobic in nature. What are hydrophobic and hydrophilic? Hydrophilic means they are water loving, hydrophobic means they are water hating. Now, since grease is a hydrophobic molecule, it is generally observed that in relation to solubility of substance in solvents, polar substances are soluble in polar solvents, whereas non-polar ones are soluble in non-polar solvents. That is, like dissolves like. So in this aspect, okay, since grease is hydrophobic and grease is also non-polar, whereas water is a polar solution, grease is a non-polar solution. But when you add a cloth which has grease in it and try to wash it with water, does the stain goes? No, it remains there because grease is non-polar whereas water is polar. So it doesn't dissolve. So on this basis, it was later reduced that polar substances are soluble in polar solvents, whereas non-polar substances are soluble in non-polar solvents. That means like dissolves like. Okay. Boiling point of alkanes are different. Okay. From which it is clear that there is a steady increase in boiling point with increase in molecular mass. So it is seen that the boiling point of different alkanes is different, and it is in such a way that as you go on increasing the molecular mass means carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, as you go on increasing the number of carbon, the boiling point also increases. And this is due to the fact that intermolecular van der Waals forces increases with increase in the molecular size or the surface area of molecule. So this is because the van der Waals force, okay, it increases as you increase the size and the surface area of the molecule. Now you can make an interesting observation by having a look on the boiling point of 3 isomeric pentanes. So here you have a boiling point. Okay, now let's see the boiling point of 3 isomeric pentanes here from this till this. Okay, now what are the boiling point? These three. It is 282, 300, 309. There is a slight difference in their boiling point, but their molecular formula or molecular mass is same. Now why there is a change? Because of the structure. Okay. Now that having continuous chain of 5 carbon atom has the highest boiling point, whereas the other two with branch chain structures have lower boiling point. So this states that as you increase the number of branch chains, the molecule attains a shape of a sphere. This results in smaller area of contact and therefore weak intermolecular forces between spherical molecules, which overcome a relatively lower temperature. So as you increase the branching, your boiling point decreases. Okay, this is because the van der Waals forces of interaction decreases. Chemical properties. As already mentioned, alkanes are generally inert towards acids, bases, oxidizing and reducing agents. So alkanes, they are inert, as I already told you in this starting only. They doesn't react with acid, bases or any other reagents. Okay, however they undergo following reaction under certain condition, but still they undergo some reactions under certain special condition. Now substitution reaction. One or more hydrogen atoms of alkenes can be replaced by halogens. Okay, nitro group and sulfonic acid. So in an alkane, you can replace one or more hydrogens by halogens, nitro group or sulfonic acid groups. Okay, now halogenation takes place either at higher temperature or in the presence of diffuse sunlight or ultraviolet light. Now what is halogenation? Halogenation is a process where you remove one hydrogen and in place of that hydrogen you add an halogen. Now halogen can be chlorine, bromine, iodine. Okay, any one of them can be the halogen that can be added. So halogenation means it is a process where you remove one hydrogen and in place of that hydrogen you add an halogen group. Now this can take place at higher temperature or in the presence of sunlight or ultraviolet light. Lower alkenes do not undergo nitration and sulfonation reaction. These reactions in which hydrogen atoms of alkenes are substituted are known as substitution reaction. Now, lower alkenes, they do not undergo nitration or sulfonation reaction. Okay, lower alkenes means the ones from C1 to C3. They doesn't undergo any kind of sulfonation or nitration reaction. These reactions in which hydrogen atoms of alkenes are substituted are known as substitution reaction. So in which these are called as substitution reaction because here your hydrogen is removed and substituted by another group of halogen or sulfur or nitrogen, any other group. Now as an example you have halogenation. Now here you can see you have a methane, you have a chlorine group in presence of H mu. H mu is your heat or sunlight. You get chloromethane. One of the hydrogen, C4, it became CH3. One of the hydrogen is removed and in place of that hydrogen you have added an chlorine and that removed hydrogen is taken up by another chlorine molecule to form HCl. This is what generally happens in halogenation reaction. It is found that the rate of reaction of alkanes with halogens is F2Cl2 Br2 and I2. This is how they react. So fluorine is highly reactive, then chlorine, then bromine and iodine. Okay, now rate of replacement of hydrogen of alkanes is. Now how they are replaced? Tertiary is replaced first, then secondary, then primary. Now fluorination is too violent to be controlled. So fluorination means removal of hydrogen and adding fluorine. It is too violent. Too violent means the moment you add fluorine into any alkane, it will start to take out all the hydrogens. So it is too violent to control. You cannot control the fluorination process. Iodination is very slow. Fluorination is too fast. Iodination is too slow. Iodination is very slow and a reversible reaction. Reversible reaction means once you convert your alkane into an iodide halogen, that means iodomethane. Okay, this is iodomethane. You can convert it into methane and iodine. So it is a reversible reaction. It can be carried out in the presence of oxidizing agent like HiO3 or HNO3. Now the reversing process, it can be done using HiO3 or HNO3, which are oxidizing agent. Now halogenation is supposed to be via free radical chain mechanism involving three steps, namely initiation, propagation and termination. Now the halogenation process, you have a mechanism to that, and this mechanism takes place in 3 steps, namely initiation, propagation and termination. Now what is initiation? First we'll see them in the mechanism format. So first one is your initiation reaction. Now in initiation, what happens is the reaction is initiated by homolysis of chlorine molecule in a presence of light or heat. Now what is homolysis? Your Cl2, it is converted into Cl. Now homolysis means breaking of this molecule into equal halves. Equal half means each of the chlorine molecule will get 1 electrons. Okay, and this homolysis takes place in presence of light or heat. That is, the Cl bond is weaker than the Cc or Ch bond. This Cl bond is weaker, okay, and hence it is easiest to break. So it is easily broken. This is what initiation is. Now propagation means chlorine free radical attacks the methane molecule and takes the reaction in the forward direction by breaking the CH bond to generate methyl free radical with the formation of HCl. Now here what happens, one of this chlorine free radical, okay, that radical will come to your methane molecule. Okay, this is your methane molecule, right, CH4. What it will do is, one of this chlorine radical or free radical, it will come and attack the CH bond, one of the CH bond, and it will break this. Okay, once it breaks, that Cl molecule will take up this hydrogen and form the HCl. Okay, the Cl free radical, one of the Cl free radical, it will come and attack this hydrogen and break this bond, forming HCl molecule. And what will happen is, one of the electron will remain with the CH3, so it will become CH3 ka free radical. Now the methyl radical thus obtained attack the second molecule of chlorine to form a CH3Cl with the liberation of another chlorine free radical by homolysis of chlorine molecule. Now here what will happen, this CH3 will attack the second Cl radical, second molecule of chlorine, that is, this CH3 will attack another Cl compound, okay, and it will break this, take one of the Cl with it, forming a chloromethane and leaving the Cl radical. This Cl radical again will go and form a methyl group. Again this methyl radical will break this Cl and this chain will continue. Okay, and the chlorine and the methyl free radical generated above repeat the steps respectively and thereby set up a chain of reaction. So this will keep on continuing. Now the propagation steps are those which directly give principal products, but other propagation steps are possible. Many other propagation steps are possible. Okay, and may occur. Two such steps given below explain how more highly halogenated products are formed. So propagation, these two steps can be continuously occurring. That means here this methyl group will break this Cl molecule, take one Cl, leave one Cl, this Cl will go and attack again another methane, form a methyl radical, again that will attack this. So this chain will go on continuing, but there is a possibility that there can be, this is one propagation step, but there can be many other steps which are possible for the propagation. Okay, amongst them some are given here. You have a chloromethane and your methyl radical. Again what will happen, one more hydrogen will be removed by this radical forming HCl. You will have another methyl radical, this will break, it will form CH2Cl2. Again one radical is given, this will again continue. Now how to stop them, because if you keep on doing them, this will continue like this. Now how to stop them? Last is the termination step. Now the reaction stops after some time due to consumption of reactant and or due to following side reactions. Now how you will stop the reaction? First step is, the reaction will stop after the consumption of reactant. After all the reactants are completely utilized, the reaction will stop, or it can stop with the following reactions. Okay, following side reactions. First is, both the Cl radicals will combine and form a Cl chlorine molecule, or both the methyl radicals will combine and form an ethane, or it will form your chloromethane. So C, that is the third option, the one of the product is formed but free radicals are consumed and the chain is terminated. So this is the one which is commonly seen where the chain is terminated. And the above mechanism helps us to understand the reason for the formation of ethane as a byproduct during chlorination of methane. Now this will help us to understand why there is a formation of ethane when we chlorinate a methane. Okay, that is usually a part of the termination reaction. Okay, so for today's video we will stop it here. For next video we will continue with the remaining reactions. So thank you for watching my video. Please do like, share and subscribe to our channel.